Hi, I'm Herb Gross, and welcome once again to our Math as a Second Language video series, where today we'll be discussing the division of mixed numbers. Now, mixed numbers are a problem in their own right, getting used to the idea of the notation and the like. But what's interesting is that, and I've mentioned this before in other contexts, is that division is usually the one operation that we learn last, and at the same time, it's one of the most important in the sense that it's what we use whenever we want to find how fast something is changing. Remember, rate, ratio, rational number, dividing. And it's the operation that students tend to learn the most mechanically, whether it's the whole number algorithm for division, whether it's the invert and multiply rule. And in mixed numbers, people look at it sometimes and say, oh, I can do that, but they have no idea what it means. So let's just look at an example. Let's suppose we have a problem, 4.5 divided by 3 3/4. And you know it's a division problem. You might not know why anybody in the world would want to do this problem, but you also know that we can convert every mixed number into an improper fraction. So 4.5 is what? 2 times 4 is 8, plus 1 is 9. That's 9 halves. 3 3/4, 4 times 3 is 12, plus 3 is 15. That's 15 fourths. So now we've translated the mixed number problem, 4.5 divided by 3 3/4, into the improper fraction problem, 9 halves divided by 5 fourths. Now we know, whether we understood it or not, that to divide we invert and multiply. In other words, you change the division sign to a times sign, and you invert the number after the division sign. It becomes 9 halves times 4/15. We know how to multiply. We multiply across. We get 36 over 30. That reduces to 6/5, which we also could have got by doing something like this. Either way. And 6/5, that's the right answer, but it's the wrong language. 6/5 in the language of mixed numbers is 1 1/5. Boom, we have the problem solved. Now, whether we understand what this means or not is another issue. Now, again, the definition of division never changes. In other words, as soon as we see this, we know that the answer we're looking for is what you have to multiply 3 3/4 by to get 4.5. And if we even understand that much, notice how we can get an estimate right away. We know that if we multiply 3 3/4 by 1, we're going to get 3 3/4, which is less than 4.5. If we multiply it by 2, we're going to get a big number because 2 times 3 is already 6. So the answer we're looking for is between 1 and 2, and 3 3/4 is a lot closer to 4.5 than it is to 6 something or 7 something. So we kind of get the feeling that at least 1 1/5 is a reasonable answer. But what's the way that we know for sure? If this is the right answer, what should happen is this is the number which, when multiplied by 3 3/4, equals 4.5. So we'll just do it. We'll take 1 1/5, multiply it by 3 3/4, and see if we get 4.5. 1 1/5 is 6/5. 3 3/4 is 15 fourths. We multiply. 6 times 15 is 90. 5 times 4 is 20. 90 over 20 is the same as 9 halves. Or you can write it as 4 10/20 by division as a mixed number, and that's 4.5, which is exactly what it should be. Now, I've been harping on the fact that by using the cornbread model, and using pieces of cornbread instead of fractional amounts, makes things intuitively easier for students to visualize, because they'll see a whole number of pieces as opposed to a whole number of fifths or sevenths or eighths, etc. So using the cornbread model, all we would do is we would assume that 4.5 and 3 3/4 are modifying cornbreads. And so what you want to know is how many times bigger is 4.5 cornbreads than 3 3/4 cornbreads. Well, with the denominators of 4 and 2, we see it would be nice to have each cornbread pre-sliced into 4 pieces. Now, why would that be nice? Well, 4 is divisible by both denominators, the 4 and the 2 over here. So let's translate now from the problem being stated in terms of cornbreads into now being stated in terms of pieces, and watch what happens. See, 4.5 cornbreads, well, each cornbread is 4 pieces, so 4 cornbreads would be 4 times 4, which is 16 pieces. A half a cornbread is 2 more pieces. 16 pieces and 2 pieces are 18 pieces. So in other words, 4.5 cornbreads is equivalent to 18 pieces. 3 3/4 cornbreads, well, 4 pieces to a cornbread, 4 times 3 is 12. That's 12 pieces, plus 3 more is 15. So now, what was 4.5 cornbreads divided by 3 3/4 cornbreads, in the language of cornbreads, becomes in the language of pieces, 18 pieces divided by 15 pieces, which is just the same as 18 divided by 15, which is 1 3/15. And the answer is the same, 1 1/5 that we got before. That pen is running out of ink, so we'll try another one. Here's the beauty. If this problem here bothers you, but this one doesn't, it's a language problem, because this is the problem stated where the implicit noun is cornbreads, and this is the same problem stated when the implicit noun is pieces of a cornbread, where a piece is one of what it takes 4 of to make the whole cornbread. Now again, people say, well, that's nice, but why in the world would I ever want to be dividing 4.5 by 3 3/4? I'm very happy that the answer is 1 1/5. Where am I ever going to use this? And this is again where you want to use the quantity idea rather than a number. Let these numbers start to modify units that we're familiar with. For example, when we talk about dollars per pound, which is it's a rate, it means what? Dollars divided by pounds. And that tells you dollars per pound. So for example, if you spend $6 for 3 pounds, see, $6 per 3 pounds, all you would do is you would put the 6 here and the 3 here, just as we did down here. And then how do you divide? You divide the 2 adjectives, 6 divided by 3, and the division sign gets replaced by per, so it's 6 divided by 3 is your adjective, dollars per pound is your unit, your noun, 6 divided by 3 is 2. In fact, my guess is you would do this problem almost without thinking about it. If it was $6 for 3 pounds, almost in your head you say, oh, that's $2 a pound. Now, the interesting thing is that dollars per pound always means dollars divided by pounds. One of the talks we used to give was called Nouns Are Your Friend. See, when you look at dollars per pound, it's telling you exactly what to do. It's the number of dollars divided by the number of pounds. And this recipe doesn't change regardless of what the adjectives are. In other words, if the adjectives are whole numbers, as they were in $6 for 3 pounds, that's fine. But what if it was $4.50 for 3 3/4 pounds? Doesn't matter. It still says what? Divide the number of dollars by the number of pounds. Okay, so we take $4.50 and we're going to divide that by 3 3/4 pounds. How do you divide 2 quantities? You divide the 2 adjectives. See, 4.5 divided by 3 3/4. That was the problem that we started with, where we knew that the answer, we already know that answer, and the unit is dollars per pound. And since a dollar is 100 cents, I guess we can say that this is $1.20 per pound. Now, again, notice if you understand what this says, we know right away that the price is more than $1 a pound, because if it was $1 a pound, 3 3/4 pounds would only cost $3.75. We know it's less than $2 a pound, because if it was $2 a pound, it would be over $6. So we know the answer is between $1 a pound and $2 a pound, and it's closer to $1 a pound, so this answer is at least plausible. Now again, to show you the adjective-noun theme here, and how we can change mixed numbers into whole numbers, notice that the denominator here is 4. That means we're talking about quarters of a pound. Let's change the noun now from pounds to quarters of a pound, and we'll just call a quarter of a pound a fourth. You have 3 3/4 pounds. What does that mean? Well, written as an improper fraction, that's 15/4 pounds. See, 15/4. Now, the whole 3 3/4 pounds costs $4.50. That's 450 cents. So if 15/4 costs 450 cents, 1/4 costs what? 450 divided by 15, that's 30 cents. Okay? So each quarter of a pound is costing you 30 cents. So a pound is what? 4 quarters. So if each quarter is costing you 30 cents, 4/4, which is a whole pound, is 4 times 30, and that's $1.20. Same answer as before, but notice how the fractions have disappeared. You know, there's another way we could have done this that I think is kind of interesting. In this problem here, notice that if we were to multiply both sides of both of these numbers, remember that we can always assume there's a division sign here. When you multiply both numbers in a rate by the same number, you don't change the rate. Now, to see that in terms of this problem, this says for every 3 3/4 pounds you buy, you're going to pay $4.50. So if you were to buy 3 3/4 pounds 4 times, you would be paying $4.50 4 times. Now watch what happens. Same arithmetic as before. If you multiply 4.5 by 4, again, 4 times 4 is 16, 4 times a half is 2, 16 plus 2 is 18. You'd be paying $18 for how many pounds? 4 times 3 is 12, 4 times 3/4 is 3, 12 plus 3 is 15. Here's the interesting thing. When you look at, again, another example here, 4.5 divided by 3 3/4 looks rather complicated, but when you change to this, it's still the same rate, isn't it? In other words, this looks threatening. Well, this may look threatening, but not nearly as threatening as this. And so you see the language problem again. In other words, you can convert any mixed number problem to a whole number problem just by choosing your unit appropriately. And by the way, another thing that people may ask is, but what would you do here if all you knew was you were taking 4.5, dividing it by 3 3/4, and you didn't know that the units were dollars and pounds? What would you do then? And the answer is, I would do exactly the same thing. See, even without the nouns here, we already know that in a rate, you don't change the rate by multiplying both numbers by the same non-zero number. So without even making reference to dollars and pounds, I simply say, to get rid of the denominators, I'll multiply both of these numbers by 4. And you see what's going to happen. I get exactly the same steps that I had before. The 4 multiplied by 4.5 still gives me 18. The 3 3/4 multiplied by 4 still gives me 15. So once again, this problem, which is sort of scary, is now replaced by this problem, which is equivalent to this. This, in a way, is easier for us to work with than this, and we see right away 18/15 is the same as 1 3/15. 3/15 is the same as 1/5, and we get the answer that way. So again, I'm not trying to show you anything new here. I'm not trying to show you that you can't divide mechanically and the like. All I'm trying to show is again, the power of the cornbread. Just an extra tool that if you replace these fractional parts by pieces, fractional problems very often become whole number problems. I think this is a good place to pause for the day, and so we'll come to our practice problem that signifies the closing of each session, and our practice problem today. And remember what we do. You read the problem, pause the video, do the problem, and then come back and look at how I solve the problem. Compare the two solutions or whatever you want to do. So the practice problem today is, moving at a constant speed, an object travels 102 3/4 miles in 2 2/5 hours. Express the speed of the object in miles per hour. Okay? Messy numbers, but keep in mind the concept is the same as what we've just been talking about throughout this lecture. Okay? Now, in solving this problem, it's always a good idea, and this is why you need a number sense. Whether you have a calculator, doesn't matter. You still need a number sense, because even with a calculator, you can press the numbers in incorrectly, and you get an answer that may not make sense, but if you're doing it mechanically, how do you know what makes sense and what doesn't? All you say is, this must be right, because my calculator doesn't make mistakes. So it's always a good idea to get an estimate of your answer even before you start. So I call it a reality check. We're looking for miles per hour, so it's the number of miles divided by the number of hours. See, in this particular problem, the units are miles and hours. But the problem, okay? Now, 102 3/4 is pretty close to 100, and 2 2/5 is pretty close to 2 1/2. So the answer to this problem should be approximately 100 divided by 2 1/2. That's the same as 100 over 1 divided by 5 over 2. To divide, we invert and multiply. This becomes 100 over 1 times 2 2/5, 2 over 5. 100 times 2 is 200. 1 times 5 is 5. 200 divided by 5 is 40, which we also could have got by doing this. So the approximate answer is 40 miles per hour. So before we even start this problem, we know that the answer has to be somewhere in the ballpark of 40 miles per hour. That's a nice thing to know in case you do make a computational mistake. Well, now let's do the problem exactly. And let's use the trick that we talked about. Instead of worrying about improper fractions, and instead of worrying about how you multiply 2 2/5, what you multiply it by to get 102 3/4, let's immediately turn this into a whole number problem. Look at our denominators here are 4 and 5. So if I were to multiply both of these numbers by 20, the fractions would disappear. See, in other words, if I multiply 102 3/4 by 20, the 20 multiplies the 102, which will give me 2,040. The 20 multiplies the 3/4. 4 goes into 25 times. 5 times 3 is 15. That gives me 15 more. So in other words, this would become 2,055 miles. Okay? This would be what? I multiply by 20. Okay? So this would become 20 times 2 is 40. 20 times 2/5 is 8. See, 20 times 2/5 is 8. So this becomes 48. So what we wind up with is 2,055 miles divided by 48 hours is 42 39/48 miles per hour. And that comes in pretty close to what our reality check said. We said the answer should be around 40. Now, there's lots of numbers around 40, so we're still not sure that this is right. But at least we know we're in the right ballpark. And assuming that we haven't made a mistake, notice that the statement 102 3/4 miles per 2 2/5 hours can be stated as a whole number problem by saying you went 2,055 miles every 48 hours. Okay? And hopefully the message is starting to get through here that the adjective-noun theme, our Cornbread model, can be used from pre-kindergarten all the way through graduate school in many respects, in a step-by-step seamless transition where you're always dealing with whole numbers. At any rate, this brings us to the close of today's presentation. I hope to see you all again next time, and until next time, stay well, be happy.